In this video, I'll be going through the solution to the apartment applicant's practice exam. To start, I'll have three files: the R template, the Microsoft Word template, and the project statement. On the real exam, you'll get a printed out project statement, and so you can print it out yourself while you're practicing. I'll read the project statement from beginning to end. In this video, I'm going to skip over the general information for candidates because this is the same for all of the practice exams. The business problem is that your client is a property management firm in New York City, and they need you to help them attract more tenants to their apartments. This will help them to increase their profitability by signing more leases. The data is the number of rental applications along with the physical characteristics of the apartment. Some data cleaning was performed in advance. The data dictionary at the end of this document describes the available variables. The target variable applicants counts the number of people who filled out a housing rental application within the given month for each apartment building. Only vacant apartments are included. Let's take a look at the data dictionary to see what this exam will look like. Okay, I see that there are a lot of variables here. First of all, I see that the first variable is called applicants, and it's the total number of people who apply for a lease at that apartment building, including all apartment units. Okay, so there's some complicated definitions, and there are a lot of variables. Let's go read the rest of the project statement. There are several apartment layouts, such as a studio, convertible, one bedroom plus dens, or 2-bedroom or 3-bedroom residences. Each layout has a different size and number of bathrooms. In addition, each building, depending on whether it's a single-story residential house or multi-story apartment high-rise, has a different number of units in the building. The residential houses have only one unit, whereas the high-rises can have up to 5 in the same building. Your client needs these results to be at the per unit level. The target variable will need to be transformed so that instead of counting the total number of applicants in each building, it counts the number of people per unit. Fortunately, the other variables need no adjustment. The sale price is the same for all units in the same building. All units were also given the same rating of interior and exterior quality, have the same number of bathrooms, and same sizes of living and lot area. So this sounds complicated. I believe that so let's look at the data dictionary. Okay, so I see applicants is the total number of people who apply for a lease at that apartment building, including all apartment units. And then the sale price is the sale price for each apartment unit. Okay, so I imagine that there's an apartment building that has 5 units, and each unit is the same layout, meaning that it's the same size, it has the same number of bathrooms, it has the same selling price, and so forth. So then this is the total number of people who apply for any unit in that building. So if there are 10 applicants, it could be that 2 people applied for each of the apartments in the building. So 2 times 5 would be equal to 10. Okay, so I see the sale price, number of units, the year sold. It's the year that the apartment building was sold, month sold, fairly explanatory. Overall quality rates the overall material and finish of the building, etc., etc. I don't need to spend all of my time reading about the data now because I assume that the specific tasks are going to dive into that. But it's worth just keeping this in mind, seeing that there are a lot of variables. I can see this is garage types. Each property should have either attached garage, basement garage, okay. So it looks like these are dummy variables. And these neighborhoods are physical locations within the AIM city limits. Each apartment building is in one of these neighborhoods. So again, these are kind of dummy variables for the neighborhood. Okay, so let's go to task 1. So I like to set up the screen so that I have the template on one side and I have the RStudio window on the other side like this. And I like to zoom out RStudio so that I have a larger workspace. I go to Appearance, Zoom, and I put this at about 80%. This just makes the monitor a little bit larger, which will help to save you time. Let's go to the task 1. Okay, your assistant has done some preliminary analysis, which is scattered throughout the RMD file. To save you time, when no changes need to be made, there is a comment, no changes needed. In places where you need to fill in your own values, uppercase variables are used, such as variable name as placeholders. Specific tasks. Task 1, 5 points. Okay, before I start going through all of these tasks, I'm going to take a minute and read through them just so that I can see what I have to do. This will help me to prioritize my time so that I don't run into the situation of getting to the very end of the exam and then finding out that there are 60 points worth of tasks that I have to complete in only a few hours. I want to know what I have to do so that I can use my 5 hours and 15 minutes as efficiently as possible. So I see first task, 5 points. Okay, provide summary of the target variable. Just looks like data exploration. Easy. Second point, more data exploration, 10 points. Third, 5 points, use insights from marketing manager. Okay, sounds like a communication task. Looks kind of complicated. Task 4, inspect some variables. Looks like more data manipulation. Task 5, choose a response distribution. Oh, that sounds like a GLM. Task 6, fit a GLM. Okay, there's a GLM on this exam. Task 7, stepwise AIC selection. Okay, fit a lasso, create a bagged tree, 10 points. Okay, I want to make sure that I give myself plenty of time for these modeling questions. 5 points, fit a random forest. 10 points, compare model performance. So this is really focusing on the modeling because I see there's 10 points plus 5 is 15, plus 10 is 25, plus 5 is 30, plus 5 is 35 points, 45 points. So there are a lot of points just for modeling, and I need to make sure that I give myself time to complete these tasks. So going back to task 1, and I haven't even started yet. I've been working this whole time and I haven't even started task 1. But that's intentional. I know that investing some time up front is going to save me time later on. So task 1 is to provide a summary of the target variable. Provide a summary statistics for applicants and num units. So let's first of all load the data, and I see that they give me some code snippets. I'm going to skip over these for now because I just want to see the summary statistics. So I will do glimpse of DF. Okay, and I see the data here. There's applicants and num units. I also want to see a summary of applicants. Okay, so I see applicants goes from 0 to 7, and sale price goes from 35,000 to 700 to about 800,000. So first of all, the data consists of how many observations are there? 1,430 observations of apartments which have sold. This includes, well, let me say 1,430 apartment buildings. This includes, so how many total units? Let's look at the sum of DF num units. This includes 3,839 total individual apartment units. So we can look at the average in different ways. We could look at the average number of applicants weighted by the number of units, or the average applicants that's unweighted. So if I want to do the weighted average, I could do sum number of units times DF applicants divided by the sum of DF num units. I can see this is about 3.6. We are interested in the number of applicants per unit. And so we use a weighted average of applicants by num units. See that this is 3.6. If you wanted to use dplyr to do this calculation, you would go df and then summarize average is equal to the sum of applicants times num units divided by the sum of num units. Part 2. Choose to use either a histogram or a bar plot to visualize the number of applicants and the number of units. Your assistant was not sure of which type of graph to use. These are labeled as graph A histogram, graph B bar plot. Only include one in your report and explain why this type of graph is appropriate. I can see here that there's a histogram and the bar plot. The histogram shows the number of applicants on the x-axis and the count on the y-axis. So the count is actually the number of rows in the data. And if you see here, one row corresponds to a specific apartment building, which has a specific sale price and a specific number of units in that building. However, the project statement asks that the target variable will be counting the number of units. So if we look at the bar plot instead, we'll see that the y-axis shows the total number of units as opposed to just the number of rows. So this is the graph that we want to include. So I'll right-click and then use the speed keys, Alt H V. Let me try that again. Alt HVSD, enter. And then I'll explain the histogram is incorrect because it shows the count of the number of records instead of the number of units on the y-axis. The bar plot below shows the total units in each apartment building, which is what the client asked to see. And the applicants range from 0 to 7. From 0 to 7 on the x-axis. Task 2. Explore the predictor variables neighborhood sale price, and overall qual. Explore these predictor variables. Apply any transforms or adjustments necessary, and comment on whether or not you expect each variable will be important in predicting the number of applicants. Decide on whether overall qual should be categorical or ordinal, numeric. Note, you don't need to transform square feet or GR living area at this time. Let's go to the data dictionary and look at these three variables. First of all, I see the sale price. This is the sale price of each apartment unit. I need to scroll down to the end to find the neighborhood sale price. This is the mean sale price for all units that are in the same neighborhood. Then there's overall qual, which rates the overall material and finish of the building on a scale from 1 to 10, with 10 being the best and 1 being the worst. So immediately I could think, as the external quality is higher, you'd also expect the sale price to be higher. When an apartment is in an expensive area, the mean sale price of other apartments around it will also be higher. And so you could see how these would be related to the number of people who would apply to be in an apartment. So let's go to the data. For task 2, I see that they give us some code here. It says no code changes are needed. And then this code calculates the weighted average with num units as the weights. So if I run this, I see the mean number of units is about 4,000. The mean sale price is 181,146. And this is weighted by the number of units. I can compare that with the unweighted sale price, which has an average of 181.69. So 181.69 versus 181.46. So there's a slight difference there. Similarly, the overall quality, when you use the weighted average, is 6.06. External quality, overall quality is a mean of 6.082. So 6.082 versus 6.06. So I'll just comment on that first. Because the client asked us to use the number of units as the weights, I'm using the weighted averages as opposed to the straight averages. The mean number of the mean sale price is $181,146, and the mean overall quality is 6. 0.06. Now let's create some graphs of these variables. I like to always look at the histogram to get a univariate picture. So I'm going to go up to the template code that they give to us. I can see there's create a box plot, create a scatter plot, create a histogram, or create a bar plot. So let's go ahead and create a histogram. And I'll just replace variable here with the number of units. And so I can see the number of apartments which have the different number of units. So most apartments only have 1 unit in the building, but some apartments have up to 5. The number of units ranges from 1 to 5, with most buildings having 1 unit. And to paste this graph, I right click and hit copy, Alt H V S D enter. Now let's look at the sale price distribution. So here's the distribution, and this is not weighted by the number of units. This is just the unweighted graph, but I can still see that it is right skewed. So the sale price is positive and right skewed. The below histogram shows the unweighted distribution. Now let's paste Alt H V S D enter. So to correct this skewness, I apply a log transform. There's one other variable that we want to see though, and that's the mean sale price, neighborhood sale price. Okay, so I can see that this has fewer values. Let's look at the project statement again. Explore the predictive variables, apply any transformations or adjustments necessary, and comment on whether or not you expect each variable will be important in predicting the number of applicants. So what I would do is I would want to adjust the sale price for the average sale price in that neighborhood. So I would want to see the relative sale price. So the way that I'll do that is I'll say, well, first I would just look at the histogram of sale price divided by the neighborhood sale price. So this would tell you if an apartment is expensive relative to its neighbors. And you can see that a value of 1 means that that apartment is priced similarly, and a value above 1 indicates that that apartment is more expensive than its neighbors. So I'll just say this. I adjusted the sale price so that it shows the relative price to other apartments in the same neighborhood. I did this by dividing by the mean sale price of the neighbors. Then I applied the log transform. See, because this distribution is still right skewed, and so I want to divide by the mean and then take the log. So let's create a new variable. I'll say df is equal to df and then mutate relative log sale price is equal to the log of sale price divided by neighborhood sale price. And then I want to drop the original variables. Okay. And then I'll say, then I removed the original sale price and neighborhood sale price variables. Comment on whether or not you expect each of these to be important in predicting the number of applicants. Well, I would expect that apartments that have a low price relative to their neighbors would be most desirable. It's not enough to just say apartments with low prices are going to be in high demand and have a lot of applicants, because they could be in an inexpensive neighborhood. I expect that this relative sale price will be predictive of demand, and that apartments which are relatively less expensive than their neighbors will have many people apply for them. The other predictor variables, like the number of units, so I'll say the number of units is not a predictor variable, but a weighting variable. When an apartment has more units, there will automatically be more people who apply, just because there are more buildings, more units that they can apply for. And that is it for task 2. Task 3, use insights from the marketing manager. The apartment's marketing manager has given you info which will be useful for your predictive models. This is based on their experience of leasing apartments for the past 10 years in New York City. Using the below facts, along with the data dictionary, engineer 3 additional features and explain your reasoning in non-technical language. You don't need to create graphs or calculate statistics. Take total square feet, GR living area, total bathrooms, lot area, overall qual, and full bath, and combine them with sale price to engineer 3 new features. If you made any transformation to sale price, then use this adjusted variable instead of the original variable. When it comes to demand for apartments, a common saying is location, location, location. That is to say that the neighborhood makes a big difference in the price and the number of people who apply. Space is expensive in the city. Tenants are always looking for good value in the cost per square foot. Demand is seasonal. Most apartments that are near universities change hands during the fall and the end of July and August, because most leases are for 12 months and people are required to find housing at the beginning of the school year. The appearance and overall quality of the building and cleanliness make a big difference. People like newer apartments which are modern looking and older apartments which are well maintained. People like having their own private bathroom. Larger apartments with more residents need to have more half bathrooms and full-size bathrooms to be in high demand. Template code is provided for you to create new features. Replace the right-hand side of X and Y with other feature combinations which you wish to use. Change the name from new feature to a descriptive name. There are a lot of words to sort through, so let's slow down and take it one step at a time. The main point is to use insights from the marketing manager. We now need to create 3 additional features and explain the reasoning in non-technical language. So we don't need to create graphs or come up with any statistical reasons. It's enough to just take this marketing manager's word. So let's immediately just go to the data and use our common sense to try to come up with 3 features. So let's, again, just look at a glimpse of the data, and then look again at the data dictionary. So let's just consider this first point here. When it comes to demand for apartments, a common saying is location, location, location. That is, the neighborhood makes a big difference in the price and the number of people who apply. That is to say, you could create a feature that is a flag maybe for high demand neighborhoods, or conversely, a flag for really low demand neighborhoods. Like maybe people like to be near the city to have a short commute. So what you could do is you could look at something like the price relative to the neighborhood, and then choose a feature that flags like the very expensive or inexpensive neighborhoods. Space is expensive in the city. Tenants are always looking for a good value in the cost per square foot. That's interesting. So what about if we created a variable that was cost per square foot? So we have here the sale price, and we have the total living area in square feet. So let's say df, and then is equal to df, and mutate cost or sale price per square foot is equal to sale price divided by total square feet. Okay, let's look at this next one. Demand is seasonal. Most apartments that are near universities change hands from the fall, the end of July and August. So let's create a flag that says student apartment is equal to if else. This is going to be based on the month that the apartment is sold. So if the month sold is equal to July or August, so if it's equal to 7 or month sold is equal to 8, then I'll say yes. I'll just say 1, or else I'll say 0. Okay, now that's 2 features. We just need 1 more. So people like having a higher quality appearance, and they like apartments that are more modern looking. So you could come up with features around the quality. Maybe you could say if the quality is greater than 8, or if the external quality and the internal quality are both greater than 6. Or maybe you could look at the external quality relative to quality. The next point is people like having their own private bathroom. Larger apartments with more residents need to have more half bathrooms and full-size bathrooms to be in high demand. So what we're looking at is the number of bathrooms and the size of the residence. So we could just create a new variable called baths per square foot, and say this is equal to total bathrooms divided by total square feet. Other possibilities are you could use the general living area or the lot area as opposed to the total square feet. you could also look at not just the number of total bathrooms, but also the number of full bathrooms, or you could take total bathrooms minus full bathrooms would give you half bathrooms. So maybe that would tell you if an apartment is in high demand or not. Try other variations or combinations of these variables. The key point is that we want to be able to explain whatever we do in very simple language. So first of all, let's run this code. And I forgot to mention that we don't actually have sale price. If you remember from our previous task, we just changed this to relative log sale price. So it would actually be better if we perhaps hadn't done this. But we want to still use it as a predictor. So what I'm going to do is actually delete this part where I remove these variables. Actually, I'm going to cut it. So Control X, and then I'm going to go down here, and then once I run this code, I'll then remove the variables. And in order to run both of these sections again, I'm just going to go up to Run, and then Run All Chunks Above. So we'll run this stuff, and then run this, and now I should be able to see my new variables. So there's sale price per square foot, student app, and baths per square foot. And I would also like to see a summary. So I just want to do df select these variables, and then summary. This is going to show the unweighted averages. That's okay, as long as I'm just going to mention that it's showing the unweighted averages, which will be slightly different than the weighted averages. So using the insights from the marketing manager, I created 3 new features let me be careful here because this needs to be a non-technical language. And so a word like feature is completely meaningless to a non-data scientist or actuary. So using the insights from the marketing manager, I added the insights from the marketing manager into the data in 3 new ways. This expands on the information which was already available by taking into account some of the facts about apartments. First, I calculated the sale price per square foot for each apartment, because price will because larger apartments which have a low selling price will be in high demand. I expect that more people will apply for these. Conversely, smaller apartments which have a high selling price will be in lower demand. Secondly, I flagged apartments which are likely to have been rented by students based on when the lease was signed in July or August. Finally, I calculated the number of bathrooms per square foot. People like to have their own private bathroom, and so large apartments with greater square footage will also take into account the number of half bathrooms and full-sized bathrooms. And let me just kind of summarize this and say that this info will improve our predictive models because these calculations will take into account multiple factors at once. Warning! I make a key mistake here. I fail to add the engineered features to the actual data. Keep watching, and so that you can see how it's possible to still recover from making a glaring mistake of this magnitude. I don't catch this mistake until I get all the way to task 10, but if you keep watching the video, you'll see how it's possible to salvage your result even if there's such a mistake made. Task 4. Inspect garage type variables and make any adjustments needed. Something is wrong with the garage type variables. Each apartment should have either no garage, one that is attached to the building, a basement garage, a built-in garage, or a detached garage. However, several of the apartments have values of 0 for all garage types. This does not match the data dictionary. Remove these apartments from the data. You do not need to check the neighborhood columns as your assistant has already verified that these are correct for all properties. So let's go to the data dictionary. And we'll see here that there are several garage type variables. Each property should have either an attached garage, basement, built-in, detached garage, or no garage at all. And these variables are dummy variables in that they're either 0 or 1. The same is also true for the neighborhood variables. So each apartment is only going to be in one of these neighborhoods. It's not possible for an apartment to be in 2 places at the same time. Okay, so we're down to task 4 here. And there is no code provided. Okay, so first of all, let's just look again at the data. And okay, I see that there are these 4 garage type variables. So let's just look, there's a few different ways that we could inspect this. One way is to use the internal RStudio viewer. So you could either go up to the environment and click on this DF data, or you could highlight the DF data frame and then press let me say you highlight this, you type in view with an uppercase V, df into the console, and this will bring up the data. Or you could also just click on this data object. And now if we go over to these garage type fields, I can filter and see like which apartments have garages and which don't. And like right here, I can see this apartment has no garage attached, no garage basement, no built-in, no detached garage, and no type, no garage, right? In other words, all of these variables are zeros, which is a problem because it can't have, it has to, this is an invalid record. So how would you find this record in the data? One way would be to use a filter. So I could say df and then filter, and then I have to select these variables. Garage type attached is equal to 0, and garage type basement is equal to 0, and garage type built-in is equal to 0, and garage type built-in is equal to 0, and then finally no garage is equal to 0. And if I do this, I'll see that there are 15 rows here. And so these are all apartments which have these garage types all 0. And what did the project statement say? Remove these apartments from the data. So what I can do is, there are a few different ways that I could do this. One is to just turn this into a big AND statement. So I'll say this is equal to 0, and this is equal to 0, and this is equal to 0, and this is equal to 0. Or I could actually just say this plus this. I'll just say the sum is equal to 0. You could also use a bunch of AND operators like these ampersands. So let's say filter, the sum of these actually has to be greater than 0, right? Because we want to exclude the garage, we want to exclude the apartments which have this invalid information. So if I do this, let's just see, I get 1,415 rows. So it's excluding those 15 rows. So I could say, so now I'll save this as the object. I'll say df is equal to df and then filter. Before I do that, I'll also show you a few different ways that you could do this, because this might be a tricky problem that you might not have thought about before. So the simplest way that you could do this is you could just open up the data file in Excel, because you will have an Excel file, and you could just manually delete those records. So think of this as like your backup option. If nothing else were to work, you could just pull this open. I would want to save this as a new file. Save this as an Excel workbook, apartment apps, edit 1. All right, and then I'll just go over to, I'll create a new variable, say garages, and this is going to be the sum of the garage type variables. All right, garage type, garage type, garage type. And then this sum should always be 1, but it looks like it's not. So here are the 15 records, and then I would just delete these records. Whoops. Delete these records, save it as a new CSV file, reload that file into R, and then rerun all my prior code. Another possibility is you could use base R to get, so you could say, I want to get an index of the rows. So rows with errors is equal to, so I just want a big Boolean statement. So let's say df garage type attached is equal to 1, right? If I just do this, and then look at this vector, it's a vector of true or false values. It's true when garage type is equal to 1 and 0 otherwise. So if I just say this, like I take this vector, and then I multiply it, then I just add it to this vector. Garage type detached is equal to 0. Garage type built in is equal to 0. I think you get the idea. So this gives me the rows with errors. And then I could just say, df minus rows with errors. And I could do this, I would just do df is equal to df minus rows with errors. So that would be how you could do it using base R if you are not the sort who likes to use dplyr. Finally, I would then just type out the answer to this question to make sure that I get full points. So I inspected the data and found several records which had all garage variables listed as 0. These must be an error, and so I removed them. Let me say I found 15 records which had all garage variables. These must be an error, and so I removed them. The data dictionary says that every apartment needs to have either an attached garage, a basement garage, a detached garage, built-in, or no garage at all. However, these 15 records had zeros for all of these values. Task 5, select GLM parameters. Your assistant has begun to fit a GLM and needs you to choose a response distribution which is appropriate for modeling the number of applicants. Choose a response family from either binomial Gaussian, gamma, inverse Gaussian, or Poisson, and then complete the following tasks. Explain, prior to fitting the model, why your choice of response family is the best one for this problem. Choose a link function so that the model will be multiplicative. Choose an offset term, if any, so that the model will predict the sale price for each individual apartment unit. And choose a weighting term, if any, so that the model will predict the sale price for each individual apartment unit. So first of all, you want to look at the histogram of the target variable in order to help determine which distribution is appropriate. So let's go back to the original tasks, and we can see the distribution of the number of applicants. First, you can see that it's always positive and that it is discrete. So this automatically rules out any of the continuous distributions, such as the Gaussian, the inverse Gaussian, or the gamma. Because it's taking on 7 values, you can also rule out the binomial, which can only take on 2 values. This leaves only the Poisson distribution. Recall that the Poisson is the distribution for counting the number of events in a fixed interval of time. For instance, the number of customers who pass through a checkout counter or the number of claims in a given policy year. For this example, we're counting the number of people who apply for an apartment in a given period of time, in a given month. So first part is explain prior to fitting the model why the Poisson is appropriate. And I would just say that in words. So before fitting the model, I can rule out the continuous distributions of Gaussian, inverse Gaussian, and gamma. The target variable is the number of people who are applying for the apartment, which is discrete. And so before fitting the model, I can rule out this. There are 7 unique values. There are 8 unique values from 0 to 7. And so I also rule out the binomial, which only takes on 2 values. This only leaves the Poisson, which is appropriate because it models a number of events in a given interval of time, such as the number of customers at a checkout or the number of claims, so forth. Part 2 was choose a link function so that the model will be multiplicative. The only link function which results in a multiplicative model is the log link. The inverse of the log is the exponential, and so the resulting GLM can be expressed as a product of factors called relativities. Part 3, choose an offset term, if any, so that the model will predict the sale price for each individual apartment unit. And then part 4, choose a weighting term, if any, so that the model will predict the sale price for each individual apartment unit. So this is somewhat of a tricky question because you don't need to use both a weighting term and an offset term. For a Poisson model, you are actually modeling a rate. So for a Poisson model, the target is actually a rate, which is the number of applicants divided by the number of units. In insurance language, This is the number, the frequency divided by the units of exposure. Well, in insurance language, the units of exposure are the number of units. So the Poisson, so this is the same as using an offset term, which is the log of the number of units. And feel free to look at the theory for a Poisson model if you don't have this memorized. So in this case, this means that I do not need to use a weighting term in the model. And I would also maybe just define what an offset is. An offset is a fixed term or a variable which has a coefficient of 1. It may also be worth mentioning that the log link function is also the canonical link for the Poisson, which makes the model more likely to converge. And you can always find this out just by typing in question mark family into the console. And then you can see for each of these distributions what the canonical link is. For binomial, it's logit. For Gaussian identity, for Poisson, it's log. This is also the default argument. So in R, if you use just GLM without this part, it will just use the log link by default. Task 6. Fit a GLM to predict the number of applicants. Construct your GLM as designed in task 5 above. Use all predictor variables. The code provided will split the data into training and test sets and fit the GLM on the training data. When you are done, provide the output for the coefficients, p-values, and AIC. Let's look at the code that we have. For task 6. So let's make this somewhat bigger so that it's easier for you to read. First of all, I have to create a training and a test set. So I do that here. Automatically it says no code change is needed. I just need to run this and it will create train and test. And then it will create train X and train Y. So X is all of the predictive variables and Y is just the number of applicants. So I can say that in the report, I split the data into training and test sets and fit a GLM on the training data. So here I have to make a few different choices. First of all, I have to select the formula. On the left here, you can see applicants. This is going to be my target variable. And then there's this formula symbol, and then the dot, which refers to use all variables. And then I also have to add the offset. And this needs to be the offset term. So to fill in these values, let's quickly take the names of the data. So I'll type in names, train. I can see these are all of the possible variables that I could choose here. And we already said that the offset term is going to be the log of the number of units. Okay, and then the waiting term says remove if not used. We don't need to use the waiting term, so I'll delete this. And the family, so to find out the family, well, I already know that this is Poisson. And the link function here says link is equal to log. But if you don't even fill in this argument, it will just use the canonical link function by default, which is also the log link function. Let's go ahead and fit this model. And I'm getting an error. Why am I getting this error? It's because I'm missing this comma here. Okay, let's try this again. Okay, so there's the GOM. I have a measure of the AIC value. At this point, I definitely should have noticed that the variables that I created were not being included. I should have seen that they were added on to the end here after the neighborhood variables. It's very important if you engineer a feature that you verify that it's being included and that its values make sense. After all, if you go to all the effort of engineering a feature, you want to be sure that it has some value. If it's a linear model, you want to see that the p-value is significant. And if you are engineering a feature for a tree, you want to be sure that your variable is appearing in the tree at least somewhere, or if you're using boosting or bagging, that it's showing up as a highly important variable. Otherwise, it's a good idea to go back and just try a different feature. So how do you know which neighborhood has the most weight? If you go back and look at the template code at the beginning of task 2, you can see that there's some code included to do just that, to show you the number of total units by neighborhood and by garage type. So here I can find that the North Ames neighborhood has the most total units, 585. So I want this to be the reference level so that the coefficients are the most stable. I can also see that for the garage variables that the most common garage type is garage type attached. Similarly, I want this to be the reference level for garage type. So if I go back to the GLM, I will subtract off the variable for North Ames, and I also subtract off the garage type attached. When I did this, I was still getting some funny results. As you can see, the neighborhood sale price still has NA values. And this is basically the same problem as before, because this neighborhood sale price is unique for each neighborhood. And so it already tells you what neighborhood the apartment is going to be in, right? And so you have to also remove this variable, or else it causes the linear independency with neighborhood variables. So let's subtract off neighborhood sale price, and then look at the result. Okay, now all of the coefficients are real numbers, which is good. However, I also see that units is being included as a predictor variable, but we've already included this as an offset term, and so it's not necessary. So I'm going to remove this as well. Okay, and this finally gives us the results of the model. So I'll put this into the Word document. And I'll make this font somewhat smaller so that it's just easier to read. I use Control left bracket on the keyboard to adjust the font size. And then I need to make sure that I answer all of the questions that are from the project statement. So they said, construct your GLM, use all predictor variables. The code provided will split the data into training and test sets. When you're done, provide the output for the coefficients, p-values, and AIC. So first I will document what I did. I started by training the GLM. I made my selections for the steps from task 5. I used the log of the num units as the offset term and removed this variable from being one of the predictors. I noticed that there was linear dependency between the neighborhood columns because they formed an overdetermined system of equations, i.e., they were not linearly independent. And so I removed the North Ames neighborhood. This had the most observations, and so the intercept term, which has the base level, is the most stable. I also removed the mean sale price variable because this was linearly dependent on the neighborhood variables. Finally, the garage type variable was set so that the reference level is garage type attached, which has the most observations. So the AIC is 5,452. This is a measure of how well the model fits the data when taking into consideration the number of parameters in the model as well as the log likelihood. A higher value is better. If you ever would like to remember the formula for AIC, you can always type $AIC into the console. And you can see that here it tells you that this is -2 times the log likelihood plus k times the number of parameters. Task 7, use AIC to select features. Use stepwise selection to simplify your model. Use the forward direction and AIC as the selection criteria. When you are done, provide the following: the model output for the coefficient estimates, p-values, and AIC, an interpretation of the graphs of residuals versus fitted, normal QQ, and studentized residuals. So as we saw in task 6, not all of the variables were significant. We would like to remove the unnecessary variables to make the model more parsimonious. Task 7 says no code changes are needed. The following code will use the same formula and family from the GLM object to perform stepwise selection. So I really don't need to change anything here. I just need to press run. And this will run the step AIC procedure. And I see that it begins using all of the variables that I specified. And then it selectively removes variables so that the AIC improves. So it starts out at 5452, and then it moves to 5450, 5446. Hold them. So this is going 5452, 5448. So it's going down. 5444. So it's going down still until it goes down to 5444. So a lower AIC value is actually better in this case. So we want to make the AIC lower. So I believe that in my prior answer, I actually said a higher AIC is better, but this is actually backwards. A lower AIC is better. So let me go back to my prior question here. A lower value is better. And this makes total sense because it's k times the number of parameters, which is some positive number, minus the log likelihood. So as the log likelihood gets really large, it makes the AIC lower, which means that the model is a better fit. So let's go back quickly and just see which variables did this remove. Well, this resulted in a model that has all the p-values showing up as being significant according to the hypothesis test. And then the final GLM here, I can see has an ASE of 5,444. Let's just copy this into Word. The step AIC procedure begins with all of the variables that I used in task 6 and removes those which are not improving the AIC. And I actually got an error here. This is a common mistake. It's when the clipboard covers, when I copy info from the clipboard and it copies too much information. So I can fix this by pressing Control-Z and then going back to RStudio and then just being careful when I copy to just include the info up to this call part. Now pressing Control-C and then going back and pasting again. And now you can see that it's not including extra info. So how do we interpret this model? Well, recall that when you have a log-link function that you can interpret the coefficients as having a percentage change on the response. So in our case, we can take the exponent of these coefficients and then calculate the percentage change that they have on the expected number of applicants. So let's copy this, open up Microsoft Excel, and then first of all, I have to change up this formatting. So I go to Data, Text to Columns, Delimited, and I'll choose a space. And then the only column here that I need is just the estimate. So I'll delete all of this and then take the exponent. So this is, beta, and this is exponent beta. And then if I subtract 1, I will get the percentage change. So let's just convert this to a number and then convert this second column, to a percentage. And then let's make this more readable. So variable impact on target on applicants. So I can see that the sale price, as the sale price increases by 1 unit, the number of applicants stays about the same. I can see that as the overall quality increases by 1 unit, the number of applicants decreases by about 5.3%. This is extremely valuable information for the client who wants to know what factors increase or decrease the number of people who apply to their apartments. So I'll copy this over to Microsoft Word and paste this. Now it's worth putting a little bit of time into this part because on the executive summary, you will almost always be asked to interpret the model in a non-technical way. And so it's useful to have this info available. So I'll say I interpret the coefficients as having a percentage change on the target variable. Because the log link function is used, I need to first take the exponent of the coefficients and then subtract 1. This shows that that as the overall qual increases by 1 unit, the number of applicants decreases by 5.3%. As the total bathrooms increases by 1 unit, the number of applicants increases by 3.7%. The other variables can be interpreted in the same way. And for the neighborhood or garage type variables, it means that if for the neighborhood or garage type variables, the coefficient represents the percentage change over the reference class base level, which is the North Ames neighborhood, and apartments which have an attached garage. For instance, in Brookside, apartments in Brookside have, let's see, there's Brookside. Brookside, the coefficient is negative. The impact is negative 21.5%. 21.5% lower predicted applicants than North Ames. And apartments that have a built-in garage have a 32% lower expected target. Okay, now we need to look at the other graphs. So we want to see the residuals versus fitted, the QQ graph, and so forth. So the quantile graph shows the theoretical quantiles versus the actual quantiles. And what this means is if the response family and link function that you chose is a good fit, then all of these quantiles will be along a straight line. As you can see, this is a very, very good fit because most of these are very close, meaning that the theoretical quantiles of a Poisson distribution are almost the same as the quantiles of the residuals from the actual model. So this is showing the studentized Pearson residuals. Recall that the studentized residuals follow a normal distribution for every type of GLM. The only exception is if you have a binomial response, in which case the QQ plot interpretation doesn't make sense. For all other distributions, if the model is a good fit, you should see that this is basically a straight line. So the QQ plot validates that my choice of the Poisson distribution and link function is appropriate. To paste this graph, I go Alt-H, BSD, enter. It shows the theoretical quantiles against the actual quantiles, which are all approximately along a straight line. There's some deviation here for the lower quantiles, which is to be expected. Now let's look at the other graphs, the residuals versus fitted. The residuals versus fitted. So this shows the predicted values on the x-axis against the residuals on the y-axis. Now, first of all, you'll notice that there are these weird patterns here, that these are kind of in like discrete lines. The reason for this is because your target variable only takes values from 0 to 7. And so the residuals can only take on discrete values as well. Ideally, you want these to be scattered around 0, which means that there'll be the same number of points above the line as below the line, and there will not be any pattern. Now, it looks like the mean here is maybe slightly positive, and so that's not perfect. And perhaps there is, well, it doesn't really look like there's that much of a pattern. As you kind of go from -1 up to 2, it looks like there might be some decreasing trend here as the residuals kind of get smaller, which isn't ideal. So the residuals versus fitted shows the, this is the raw residuals against the predicted values. This is different than the studentized residuals above, which are adjusted by the shape of the Poisson distribution. They are approximately centered at 0, although there is some decreasing trend. The residuals get smaller as the predicted values increase. Let's look at the other residuals. So here's the square root of the studentized Pearson residuals. And as you can see, there are still these zigzag patterns here because the response is discrete. And you can see that the magnitude basically stays the same. So here you can see like there's this decreasing trend. The residuals are getting smaller. But here you can see that the height above and below the center is basically the same. Whoops. So the the scale location plot below shows that there is no clear pattern when I adjust for the Poisson distribution with the studentized residuals. And here's the residuals versus leverage. So this shows you on the x-axis a measure of how much a point affects the result of the model, known as the leverage. So what you don't want to see is any points that are up here. That means that they have high leverage and that they have a high residual, meaning that they're having a big impact on the model's results. So the only points that might be concerning are number 561 and number 971. These other observations are all they're all relatively low in influence. Scale location plot shows that no points are having too much of an impact on the model results. Whoops. There are no points in the upper right quadrant of the graph. Task 8. Fit a lasso. Your assistant has fit a lasso model. Note that in R, it is not possible to specify the link function when using the GLMNet library, and so the identity link is used. Use your formula from the GLM in Task 6 for the weights and offset terms. Your assistant was confused because some of the variables have coefficients which are exactly equal to 0. Before making any changes to the code, provide a statistical explanation as to why certain variables can have coefficients which are 0 in a lasso. Then fit the model and record what these variables are. So let's look at the code provided to see what changes I need to make. So I can see here under task 8, it says the only changes needed are 1, replace weight variable with the weight variable that you used for the GLM. Well, this is somewhat of a trick because I didn't use a weight variable. So I'll just go down here and delete weights. And then 2, in the lasso formula below, use the formula from task 6. So right here, formula needs to be the formula here. So actually I should use the, well, I could, so if I used the formula from task 7, I would actually use the formula after running step AIC, which would already have removed variables. But I want to start with all the variables again, because that's what the lasso is going to do already, is remove variables for me. So this is the formula here. I'll use the log number of units as the offset, and then the other things stay the same. Finally, number 3 is use the same family from task 6. So family is going to be equal to Poisson. And if you're curious as to why this is, just type in $GLMnet. You'll see the documentation here. And the family can either be Gaussian, binomial, Poisson, multinomial, Cox, or multivariate Gaussian. But the link function always needs to be the identity link. So here we go. So we'll go ahead and run this model. And then this says, so whenever they tell you, not to make any code changes, it's important to understand what the code is doing, first of all, so that you can explain it. So here it says it fits the lasso to inspect the variables which have 0 coefficients. Note that the GLMnet library only allows the identity link. And then it says this code gets the coefficients from the lasso, which are equal to 0, and then shows the coefficients. So these are sale price, month sold, total bathrooms, neighborhood Northridge, and neighborhood Timber. So what does this mean exactly? Well, in the lasso model, what we're doing is creating a penalty term so that we remove variables. So we want to remove variables which are not statistically significant. This is known as shrinkage, and that's controlled by value of lambda. And so here I can see that lambda went from 0.01 up to 0.0001 up to 0.01, right? And basically when lambda gets larger, more variables get removed and the model gets simpler. So this automatically chose lambda by cross-validation, and then it removed those variables by setting the coefficient exactly equal to 0. So I just want to provide a basic statistical definition. So the lasso is a type of penalized regression which makes the model simpler by imposing a penalty term on the number and size of the parameters. This is a special case of the elastic net, which takes two parameters called lambda and alpha. When alpha is equal to, let me see this again. When alpha is equal to 0, we have ridge regression, which penalizes the sum of the square of the coefficients. And when alpha is equal to 1, we have the lasso, which penalizes the sum of the absolute value of the coefficients. So this has the resulting effect of setting some variables, coefficients exactly equal to 0, which removes them from the model. When I ran de lasso using the same formula from the GLM in task 6, I found that these variables were removed. These were sale price, month sold, total bathrooms, neighborhood Northridge, neighborhood timber. Let's just make sure that I've got all of these questions answered. Your assistant was confused because some of the variables have coefficients which are exactly equal to 0. Before making any changes, provide a statistical explanation as to why certain variables have coefficients which are exactly 0 in a lasso. Then fit the model and record what these variables are. Done. It's worth noting that for these types of questions, the SOA is not going to have a specific answer that they're looking for. The graders will be looking for a few different things. It would be acceptable to say the lasso helps to reduce the model error by the bias variance trade-off, because as we increase the bias, we decrease the variance, and vice versa. By imposing a penalty term on the coefficients, we can reduce the model's complexity, which improves the fit on the cross-validated training set. You could also mention that we only tuned specific values of the lasso values of lambda, and that if we wanted to make the model simpler, we could use a higher value of lambda, which would remove even more variables. The main point, though, is to emphasize the fact that when the coefficient is equal to 0, it means that the variable is not being included. And this is similar to our result from step AIC. So let's look at what the code does. Task 9 says, the following code creates 8 samples of the data. 20% of the records are taken with replacement from the data randomly. Here I can see sample 1 takes the training data and then samples 20% with replacement. This is the setting for the decision tree parameters. Make your adjustments here to test out different parameters. So here the control is setting the tree settings, which tells you how tall or how wide to make the decision trees. So if you're not sure what these parameters are off the top of your head, there's no need to worry. You can always look at the R documentation. If you remember what these parameters are, that's great. You can go ahead and just start testing out different values. To open the documentation quickly, you can either go to the console and type in question mark, the name of the function that you want, in this case, question mark R part control, or you can also just highlight put your mouse over the function and then press the F1 key to open up the documentation. So here you can see min split is the minimum number of observations that must exist in a node for a split to be attempted. Typically, these values range from about 5 to maybe 20, depending on the size of the data. In this case, we have about, how many rows of the data do we have? We have only 1,000 rows, so I would not set this to be too high. I would start with a value between 3 to 10. I wouldn't go much higher than that because there are only 1,000 observations. CP is the complexity parameter. This is used for any split that does not decrease the overall lack of fit by a factor of CP is not attempted. So there's not really a hard and fast rule for setting the CP, which is why you typically have to just try out different values or use cross-validation. In this case, I'll just start by using 0.01. maximum depth is very straightforward. This is just the number of variables that are used in the tree. If maximum depth of 3, it means that there will be 3 decision points in the tree. I'm going to set a value a little bit higher, up to about 5. The maximum depth depends on the number of variables that you have. Obviously, you can't have a lot of splits if you don't have a lot of variables, unless you're reusing the same split, which does happen for continuous variables. So in this case, you want to look at the number of columns of train, and you see that n col of train, and you can see that there are 41 columns. So you could, as a rule of thumb, you can think of the square root of the number of columns. At least that's how a random forest works. A random forest uses the default value of mtry as the square root of the number of columns. So the square root of 41 is about, it's close to 6, because 6 squared is 36. So using a value of about 5 to start is very reasonable. So I will just choose these parameters. And next you can see that all of these trees get fit, and they all use the same control settings. And then there are 8 different decision trees here. And because each tree is trained on different sections of the data, there are slightly different variations in the tree structure. And then here you can see the predictions. So tree 1 uses the predictions from tree 1, and every tree is using the test data. So all the trees are being evaluated on the same data set, but they were trained using different samples. And then here this says, update this formula to perform bagging. So note that the predictions get multiplied by the number of units, so they will need to be on the same scale as the target variable. That's actually irrelevant. So next you can see the predictions. So there are 8 different trees, and there are 8 different predictions that are all based on the test set. So the key point here is that each tree gets trained on a separate sample, but they all get evaluated on the same test data. Update this formula to perform bagging. So first of all, what is bagging? Bagging is when you take an average of several models that are trained over bootstrapped samples of the original data. The most common example of bagging is the random forest, where decision trees are used as the base learner, and then several trees are fit. Usually this is several hundred trees, and then the average is taken in order to create a final prediction. In this case, we only have 8 decision trees. This formula is set up to take some weighted average of each of the trees, which isn't what we want. What we just want is the straight average. So I'm going to delete this and say tree spread is equal to tree 1 spread plus tree 2 prediction plus tree 3 prediction plus tree 4, 5, 6, 7, 8. And then you can probably guess you just divide this whole sum by 8 in order to take the average. So this will use bagging of the 8 decision trees. So let's go back to the project statement. So first of all, they say update the formula of the predictions to use bagging and explain how this helps to reduce overfitting. Create a bag decision tree. So the code was set up to sample 8 to create 8 bootstrapped samples of the training data. A bootstrap is stands for, I believe it's bagging aggregation, where multiple samples of the same data are taken. Different models are fit over each sample, and then the average, and then the average of the model of the model's predictions is used as the final prediction. I should say this is really the result of bagging. So I'm just going to say bagging is where so I updated the formula of the predictions to use the average of the 8 trees. And I can go more into detail about how the data was trained. So I'll say 8 samples of the training data were taken with replacement. And then bagging was performed. And I'll say bagging is where multiple trees are taken, etc. The average of the model's predictions based on the test set used as the final prediction. I updated the formula of predictions to use the average of the trees. Okay, now let's fit 3 different selections of the parameters. So I would open up Microsoft Excel and create a table of the 3 parameters. So we have min bucket, CP, and max depth. And I'll say this is going to start at 5, 0.01, and max depth of 5. And I'll just think about some other variables. Like I'll just try increasing min bucket to say 10, CP. Well, if you make the min bucket larger, it will make the tree a little bit stubbier. And so you can go ahead and try lowering the complexity parameter. And then I'll just keep that at 5. And then I'll try putting CP back at 0.01, and then move the maximum depth up to like 7. And then here I want to record my performance metric. Now, what is the performance metric? They say, and record the log likelihood. Then choose the parameters which have the best log likelihood. You can see here that this ll function takes in the targets variable and predicted values, and then it returns the log likelihood based on a Poisson model. So you can just go ahead and run this and see that the live likelihood is 234. And now let's try 10.01 and 5. So 10.01 and 5. No, 0.001. And then run these sections again. And then it goes down to 234, 224, which is worse. Now let's try 10.01 and 7. And this goes to 223. So it looks like the best settings out of the three are from this first model. I fit 3 different models. I varied the min bucket, which controls the minimum number of observations in a split, CP, which is the complexity parameter, and maximum depth, which is the max height of the tree. Then I compared the log likelihood of the Poisson model based on the test set. The log likelihood is best, highest. Let me just say the log likelihood is the probability of generating the data, generating the response variable given the data and given the data. So a higher value implies that the model is more accurate. This first model with min bucket equals 5, CP equals 0.01, and max depth equals to 5 is best. And so this is what I chose. Use the graphs for a few of the individual decision trees to identify the top most important variable. This does not need to be a precise estimate, but can just be a few sentences. Explain your reasoning based on the plotted tree. You do not need to include tree graphs in the Word document. So let's look at some of these graphs. So first of all, tree 1 asks, does this apartment have central air? And then it asks, is the month sold less than 7? Is the garage type attached? Month sold, and such, etc., etc. So the key point to take in mind here is that variables that are more important occur earlier on. Because of the way a tree algorithm splits, the most important variables occur higher up in the tree. because they have the highest entropy. In other words, they divide up the training samples. They divide up the most of the training samples. And so those are the variables that are the most important. So if you look across all of the trees, you should spot a pattern. You should see that some variables consistently appear high up in the trees. So here I can see central air is the first split. Central air again is the first split. Now garage type attached is the first split, but central air is number 2. Garage type attached, but then central air. Hey, this tree looks kind of similar. They both have the same like first 3 splits, but then the subsequent splits are different. Like this is looking at months old. This tree is looking at general living area. This one also has central air as the first split, and then total square feet, central air, sale price, central air, and so forth. So if you used different features or different engineered features, you will have different answers here. In my case, I have central air as the most important in 1, 2, 3, 4, 5. So 5 out of 8 trees. So a decision tree works by partitioning, by recursively partitioning the training data based on variables which separate out apartments which have a lot of applicants from those which have relatively fewer applicants. The variables that are higher up in the tree, as well as those which appear more often, have greater predictive power, also known as variable importance. In my case, the variable central air appeared as the top split in 5 out of 8 trees. And of these trees where it wasn't the top split, it was number 2. And of the 3 trees where it was not the top split, it was still the second level split. This is the most important variable in the bagged tree model. Okay, finally, once you have chosen parameters, compare the log likelihood of tree 1 to the bagged trees. Is this better or worse? So we look back at our log likelihood. We can see here, I could take the log likelihood of just tree 1 prediction and compare that with all 8 of the trees. And I see that the log likelihood for tree 1 is just 147, which is worse than using the average of the 8 trees. So not surprisingly, the log likelihood of a single tree was lower than the average of the 8 trees. The log likelihood, I'll just say this was 147 for tree 1 under the third model as compared to 23 for the bagged trees. And there's actually one other part to this question. The first point was update the formula of the predictions to use bagging and explain how this helps to reduce overfitting. So this is really asking you about the bias variance trade-off and how that relates to model averaging. So that helps to explain why the average is better than the single trees predictions. So I will just add a few sentences here. I'll say, this improves performance because of the bias variance trade-off. Taking the average of several trees reduces the variance, right? Because variance decreases as the sample size increases, right? And the bias decreases as each tree uses different variables, and so the likelihood of a single tree overfitting, and so when a single tree overfits, this has less of an impact on the model overall, because this tree is only given partial credibility, to use some actuarial language. This is the very same idea that you will see in insurance reserving, where you might take an average of several different reserving methods. Task 10, fit a random forest and measure the variable importance. Your assistant has set up a random forest with 400 trees. This uses the same variables as the lasso model from earlier. Use the results to answer the following questions. How does the most important variable compare with the model from task 8? What are some possible reasons for these differences, if any? So we just said that the most important variable in the bagged trees was central air. So let's go ahead and run this code here. And I need to use the same formula that I did from earlier. So I'll go up quickly and copy this formula. At this point, I realized that I had actually made a very critical mistake earlier on, namely that I hadn't included the engineered features in any of the prior models. Now, this is some cause for concern. It happens quite frequently that you will have to redo a lot of your report. Fortunately, though, when this does happen, and inevitably it will, there are ways of quickly refreshing the prior work. So the way to do this first is to identify the problem. So the problem that I found was that in the data set, I was not including the features that I had added. These were sale price per square foot, student apartment. And so what I had to do is go back to all of the prior tasks and make that update. Now the way to quickly do this is to click on this task button here, and then you can move between the tasks. So I want to go back to task 3 where I engineered the additional features. And then I just wanted to check that these features were included. So I just ran df and then summary, and I could see that the student apt, bath per square foot, and sale price per square foot features were included. And then I had to go and rerun all of the subsequent chunks. So I just can either click through each of these chunks, or I can select a chunk and then press run all above, and that will just run all of the tasks that are above this chunk. Then I have to update my Word document, which is somewhat of a time-consuming process. So I have to go back, and for each of these results, I basically have to update them. So I don't need to update anything up to everything before task 3 is okay. But when I get down to task 6, fit a GLM, this model result has to be updated. So let's just delete this and then go back to task 6, fit a GLM, and then update this output. And as you can see here, that these engineered features do have significant predictive power because their p-values are less than 0.001, which is a good sign. So if you did create features and they do have significant p-values, that means that you are improving the model, which is very good. So all of my commentary here, fortunately, can stay the same, except for the AIC value. The AIC is now 5202. I can also note that my 3 engineered features have p-values less than 0.001, which indicates that they are predictive. Next, I need to update the stepwise selection. So fortunately, I can just rerun this part. And then look at the AIC. It goes to 5225. 5225. So this is actually improving the AIC. So AIC is higher. So I can see here that the AIC starts out at $5202, right? 5202, which is where this task 6 model left off. And then it actually goes to 5225 in one step. Does that make sense? Should AIC be increasing or decreasing? If you're not sure, you can always look at the formula. So again, it's -2 times log likelihood plus k times the number of parameters. So you want the log likelihood to be as high as possible. So if the AIC decreases, then that means that the log likelihood is getting better. But then it also depends on the number of parameters, right? So if you like drastically reduce the number of parameters, you will also lower the AIC. So a higher value so imagine that you had a really complicated model with like 1 million parameters, and the AIC would be really high, and it wouldn't matter how good your fit was, the AIC would be really high, so there would be a high penalty, so that would be a bad model relative to another model. Conversely, if you had a model that had very few parameters, then your AIC would be much lower. So again, you want your AIC to be lower because that favors a simpler model. So it's rather interesting that that this model has a higher AIC value. This actually makes a worse model, the result worse, because the AIC increases to 5 to 2.5. Still though, this has a simpler model, right? Because if I look at the summary of this GLM, it actually doesn't look like it's doing very much. So I can see my engineered features are still included, but it's not eliminating a lot of these values. Again, that's okay. I'm just going to continue to move forward because this is really where the time comes into play on this exam. Even if you have some result that's not perfect, it's really important to just keep moving to get as much credit as you can for every question. Okay, and now let's just look at the plots quickly. We'll have to update these. So these residuals do not look nearly as good as what we had before. Again, we're just going to keep going because we're trying to make this exam as realistic as possible. So even if I don't know, even if I know that something is not perfect, it's really important to note that. So the QQ plot indicates that my choice of Poisson distribution and link function is not a great fit. There is significant deviance along the upper and lower tails. So again, that's somewhat problematic, but I don't have time to kind of dig into this, so I'm just going to quickly update things and then move on. And if I have time at the end, perhaps I can come back and add a comment. But it's most important that you just get all of the results onto the document. And then here's the residuals versus leverage. Whoops. Let's go back to the lasso question and update the lasso. Okay, now I see these variables are year sold, total bathrooms in neighborhood Gilbert. task 9, create a bagged tree model. So you'll have to go through and update your AIC values for these different parameters. And so I've already gone ahead and done that. Well, let's just do it here. So we'll start with the first one. And we will also notice that the most important variable now is sale price per square foot. Sale price per square foot. Sale price, central error still comes up as important. Sale price per square foot. This is a great sign because this is one of the features that we customized. So I'll just rerun this and I'll see the first AIC. First log likelihood is 295. I'll go back and comment this out and switch to the second set of parameters. Rerun. 356. Let's go back up. Run this again. 343. So now it's actually this second tree model that has the best parameters. So I'll go back and make sure that I use these parameters as my final tree. So I'll go up to controls, set this to use 10.01 and 5, 10.01 and 5. And then again, we'll look here and we'll see still that it's sale price per square foot out of 7 out of 8 trees. So before it was central error that was the most important variable. Now we're seeing that it's sale price per square foot. So I need to update this question answer. Decision tree works by recursively partitioning the training data based on variables which separate apartments and have a lot of applicants from those which have relatively fewer applicants. That's all correct. This is also all correct. Now the sale, in my case, the variable that I engineered, sale price per square foot, appeared as the top split in 7 out of 8 trees. And of the one tree where it wasn't, it was second. And out of the one tree where it was not the top split, it was the second level split. This is the most important variable in the bagged tree model. Not surprisingly, the log likelihood of a single tree was worse than the average of the 8 trees. This was, let's see what it was here. It was 132. Actually, let's rerun this. It was 128 as opposed to 356. Okay, now we're caught up again. We're caught up to task 10, which was to fit the random forest. Your assistant has set up code to fit a random forest and measure the variable importance. Your assistant has set up a random forest with 400 trees. This uses the same variables as the lasso model from earlier, except num units is the weighting term. Use the results to answer the following questions. How does the most important variable compare with the model from task 8? What are some possible reasons for these differences, if any? How do the unimportant variables compare with those which had coefficients of 0 in the lasso? If there's a significant difference, why might this be the case? Ignore num units as this is different because it is used as a weighting term. So let's look at the code here for task 10. And so I want to use the same formula as I did for lasso, except I want to exclude num units, but then use the training number of units as the weighting term. This is because we can't use the offset because the random forest doesn't use a Poisson distribution. In fact, a random forest doesn't assume any type of distribution. So we just use the weighting term, which is the number of units. So there are probably alternative ways of doing this. And there would be pros and cons. The main test, though, is going to be just comparing the log likelihood on the test set. That will really be the criteria that will tell you if the model is doing a better job or not. So we'll just go ahead and run this. The only thing that I changed was just this formula. And I can see so here you can see the variable importance. So the way that this works is it looks over all the trees, just like you did in the bagged tree example, and it looks at the percentage increase in mean squared error if the variable is randomly permuted. So let's take like central error, for example. It looks over all the trees where central error appears as a split, and instead of using the actual value as being yes or no, it just randomly selects a yes or a no for every one of those trees. Then it compares the mean squared error for the version of the model that has the random central error versus the model that has the actual values in the data. And based on that, it ranks the variables as having the most influence. And this agrees with what we saw from the bagged trees example, was that sale price per square foot is the most important. We can also see which variables are not important. These are mostly the neighborhood variables, also external quality, lot area. So we can compare this with what we had from the lasso, because the lasso removes variables which are unimportant by setting the coefficient equal to 0. So these were year sold, total bathrooms, neighborhood Gilbert. So I actually don't see year sold on here, which means this is actually just showing like the top 50 or the top 30. So if it's not even shown on here, it means that it didn't even make the top 30 most important. So it's really not important at all. What about neighborhood Gilbert? Neighborhood Gilbert here is on the bottom, so that's relatively unimportant. And total bathrooms. Total bathrooms is actually fairly important in the random forest, which is an interesting observation. So let's take a shot at answering this question. First of all, how does the most important variable compare with the model in task 8? So I fit a random forest on the training data using the num units as the weight. The most important variable was the sale price per square foot, which is the same as what we found in the bagged decision trees. This is not surprising given that both models use bagging and both are based on decision trees. What are some possible reasons for these differences? Some possible reasons why these could be different. These importance rankings could be different are, one that the random forest below uses the percent decrease in MSE to rank importance, whereas our bagged trees, my bagged trees, we're just looking at the frequency and height in each tree, which is a crude measure. Secondly, the trees in the random forest are using different hyperparameters. And thirdly, my bagged tree model used only 8 trees, whereas this random forest uses 400. This allows for deeper interactions, and could be why we see the differences. As compared to the lasso, the variables are similar for year sold and neighborhood Gilbert, which are both unimportant. And I'll just say, year sold doesn't even make the top 30 in the random forest. But then we did see that total bathrooms was higher in the random forest than though as it is ranked 1, 2, 3, 4, 5, 6, 7, 8. So it's ranked 8 out of like 39. 39, which is fairly high. One possibility here is that the random forest is able to account for interactions, whereas the lasso isn't. What that means is that because the random forest is a tree-based model, it can detect when variables interact with one another. For instance, it can look at the number of bathrooms and the square foot of the apartment at the same time, whereas the lasso can only consider those two variables independently. Task 11. Compare model performance. Your assistant has provided code to calculate a Poisson log likelihood. Compare the performance and comment on the model which has the best result. Comment on 1 to 2 ways that each model's performance could be improved if you were to do this analysis again. So first of all, what is the Poisson log likelihood? This is simply the probability of generating the data given the model, assuming a Poisson distribution for the target. So you want this value to be as high as possible because that means that the model is a better fit. So let's look at task 11. And we can see they say, this function will calculate the log likelihood based on a Poisson model for the number of applicants. And what this does basically is it takes in two values, the targets and the predicted values. It sets the values equal to 0 if they are less than 0. In other words, it gives them no weight. It gives negative values no weight. If the values are, if the predicted values are less than 0.001, I'm sorry, if the values are less than 0, it uses a really small number, 0.0001, so that you can take the log. Because you can't take the logarithm of 0, it's undefined. So to avoid that, they just replace the zeros with 0.0001. What this does is it basically calculates the likelihood of generating the data given a Poisson assumption. So it takes in two values, the targets and the predicted values. And then it returns a log of a probability. So a higher value means that the model is a better fit. A lower value means that the model is a worse fit. Technically what this does is it takes the sum of the targets times the log of the positive values minus the sum of this PV0. And it has to do some fancy adjustment because it has to say if the predicted value is negative, then use a really small number. That's because you can't take the logarithm of a negative value. And so they need to replace the negative values with 0.001, which doesn't make a big difference on the log likelihood because it's such a small value. So then we can just run this code and it will take in the GLM predictions, the lasso predictions, the random forest predictions, and it will create this nice table. So here I can see that the best model is the random forest. The second best is the lasso. The third best are the bagged trees. And then lastly is the GLM. So I would say, I computed the log likelihood based on the test set for each of the models. The random forest is the best, followed by the lasso, bagged trees, and then the GLM. Comment on 1 to 2 ways that each model's performance could be improved if you were to do this analysis again. Some ways of improving that I could improve these models if I were to do this analysis again are for the GLM, I could try out interaction terms because my model used only the primary features. An interaction is when the value of the target changes, interaction is when the impact that a variable has on the target changes, depending on multiple variables at once. I could try out, alternative link functions instead of just the log, as well as the quasi Poisson distribution. This is used when over dispersion is present, which I could check by comparing the mean and the variance of the number of applicants. Basically, if the mean is equal to the variance, then the Poisson is appropriate. For the lasso, I only tested out, I could test out more values for the parameters. I could try a ridge regression model by setting alpha equal to 0, or just tune alpha using cross-validation. Similarly, and I could try out more values of lambda using cross-validation. For the bagged trees, well, I could try out more parameter combinations because I only tried 3. I could use pruning based on the complexity parameter, as well as change the splitting criteria. What did I use? What did the code use? You can go and look. You can see that it's using just the default splitting criteria. But it might be best to use maybe a different splitting value. See, the method is either one of ANOVA, Poisson, or class, or exponent. So in this case, I guess it's using Poisson, which is appropriate. Go back to the answer here. So we already have two possibilities. Try out more parameter combinations. Use pruning based on the complexity parameter. And choose the best CP based on cross validation. For the random forest, I could try use more trees as the as I only used 400. I could try alternative values for mtry as well. For all of these models, I could also change the engineered features. For all models, I could try engineering additional features because I only tried out 3. which were all predictive. And also for the lasso, I could try out interaction terms, because the lasso doesn't take these into account automatically. And I could also try adding nonlinear transformations, or smoothing splines for things like for the continuous value variables, such as sale price and quality. So there are a lot of different ways of answering these questions. Just having a few bullet points for each model is sufficient to get full credit. Task 12, executive summary. This is worth 20 points. It goes without saying that this is the most important question on the exam. You have 5 hours and 15 minutes in total, but you want to give yourself at least 2 hours just to focus on the executive summary. Even if you're not completely finished with the other questions, if you don't start the executive summary, you won't get even partial credit for your earlier tasks. So it's incredibly important that you have a complete executive summary with at least 2,000 words and clean language, no grammatical errors, clear explanations, and no technical language. The project statements clearly say, do not include technical language in the executive summary unless you explain it as if you were talking to your manager or to a sales representative or someone who doesn't have a data science or actuarial background. You will lose points if you include words like algorithm or statistical terms like cross-validation or convergence without providing a good explanation. For the other parts of the report, it's acceptable to use technical language. It's acceptable to use technical language. So your executive summary should reflect the information provided in tasks 1 to 12 as relevant to a sales manager at the property management firm. Your executive summary should include a problem statement, discussion of data, a non-technical overview of the models which you tested, your recommended solution, and a conclusion. So let's open up the template, and then what I like to do is to split the windows so that I can read over my prior work and type at the same time. So first, I will begin with a summary of the problem. So if we go back to the project statement, I can see that our client is a property management firm that needs to attract more tenants to their apartments. So our task, I will also use in the report I used I for everything, but I think it's more formal if I use our is in the executive summary. Our client is a property management firm in New York City, and enlisted our help to increase the number of people who apply for their apartments. This will increase their sales revenue by letting them sign more leases. This analysis used real data from 1,430 properties between the years of, let's look at the year sold variable, df summary year sold. It's always a good idea to start with a project statement and then just to summarize the basic facts, how big the data is, when it was collected, how it was collected, what the variables were, and so forth. The data goes from 2007 to 2011. Which represents, so we had, for each of these apartment units, buildings, which include how many apartment units, df num units, and then sum, 3,839 units. We had information on the number of people who apply for a lease, the size, number of bathrooms, size of the lot, neighborhood information, garage, overall quality, both inside and outside, the neighborhood that it was located in, type of garage, sale price, number of bathrooms, number of half bathrooms, and so forth. We used this information to construct a model which can predict how many people will apply for any given unit to help our client understand what factors contribute to the demand for an apartment. So then after I provide a simple overview, I like to go right to the findings. So I'm just going to kind of put off the exploratory work first, because when you're writing for journalism, there's a common saying, or burying the lead. When you take the most useful information and you don't write it until like the very end of the article, you want to put the most interesting information in the front of whatever you're writing to hook your audience, so to speak. That's also very important in business writing because you want to take into account the amount of time that these people are going to spend reading. If you're writing for a senior executive, they are going to want to read very quickly. They will not even read your entire report if they don't see something interesting in the first paragraph or two. So I'm going to dive right into the interpretation of the coefficients. This table from earlier still has to be updated because the coefficients changed. So I'm going to do that right now. So I'll go back to the GLM problem, to the selected GLM here. And then I have to update these parameters. So I need to go to data, text to columns. And here we go. And here you can see that these values have changed. This bathroom per square foot is throwing an error. It's because this is basically 0. So if the coefficient is basically 0, what bathroom per square foot? That's 9 times 10 to the second. 9 times 10 to the. That's a very big number. So bathrooms per square foot is having a massive impact. So this last part is taking the exponent of this number minus 1. And this is, I think they're throwing an error in Excel because it's trying to format it as a percentage. Or because it's such a big number, because you're taking the exponent of 900, which is a huge number. So that's a question mark for me. I'm not sure why that's the case. So in that case, what I would actually do if I was getting a huge coefficient like that is I would just remove the variable from the model. Because if the coefficient is that big, actually, no, I would just leave it. I would just leave it blank and then say that the coefficient came out to be that value, but the interpretation was questionable because the coefficient is so large. Because it's important to show the actual results of the model. Okay, so let's fill this in. These formatting tricks can always be somewhat tricky. So here I can see the impact on the number of applicants, and I just need to update this language. So for instance, as the overall quality increases, the number of applicants decreases by 4.85%. As the total bathrooms increases by 1 unit, the number of applicants decreases by 20.58%. The other variables can be interpreted in the same way. For the neighborhood or garage type variables, the coefficients represent the percentage change over the reference level, which is still the same. For instance, the apartment in Brookside, Brookside has a 19.71 lower predicted number of applicants than North Ames, and apartments built in garage, with a built-in garage, have a 25% lower. There was one question, the coefficient, the interpretation for bathrooms per square foot was more ambiguous because of the large size of the coefficient. So here it's definitely positive. We definitely see we see that the sign is positive, indicating that having more bathrooms per square foot increases the number of applicants. Okay, now let's try to simplify this into the executive summary. So the way to do that is just to take the table and then I would just round these to just one decimal place, and then I'll hide this value and then say interpretation. And I want to just try to think about a reasonable way to interpret this. So the intercept is remember just the base level. So you could interpret the intercept as saying that apartments which are on the North Ames neighborhood with no garage are the most common apartment, and these have 89% fewer applicants than the average. For overall quality, you see that as the quality increases, the number of applicants decrease. So number of applicants, so decrease, I'll just say decreases as overall quality increases, perhaps because customers are shy from purchasing, like luxury apartments that are too expensive for their budget. The total square feet is approximately 0. So size by itself does not make a difference, because you also need to take into account the price. The total bathrooms does. So apartments which have more bathrooms are less desirable. This could be misleading because it doesn't take the size, into account. So the way to interpret this is when you hold all other variables constant, that the impact that the variable has on the number of applicants. So this says the total bathrooms, when you hold all other variables constant, has a negative impact. So you know that apartments that have more bathrooms are also going to have larger size, and so they're going to probably have a higher price. But these variables by themselves are not that useful. External quality increases. It has, let's say, demand increases with higher quality on the outside of the apartment. This makes sense because people may look at photos of the apartment building before visiting and submitting an application. Sometimes they don't have apartments photos in the apartment itself are not available. And this is just one possible interpretation. There might not be a right answer for this type of question. What is important, though, is that you translate the statistical interpretation into some real life possibility. Central air, no. So apartments without air conditioning are in lower demand. Customers like having comforts such as AC. So these are all the garage types. So when there's so the base level here is garage type attached. So apartments which don't have an attached garage are less demanded than apartments which have one that is attached to the building. And for a no garage, so customers are don't like having, customers would prefer to have an attached garage than to having none at all. So now the neighborhood Dale has a negative 40% impact. So this means that apartments in the Dale neighborhood have 40% fewer applicants than those same apartments if they had been in the North Ames neighborhood. When adjusting, it goes without saying that all of these changes are after holding all their other variables in the model constant. The same with these other neighborhoods. So apartments in this neighborhood, in Gilbert and Brookside, have 20% fewer applicants than those same apartments than those in North Ames. I'll just copy this down for each of these and just change the name. So this is Gilbert, Meadow B, and North Ridge and North Ridge Heights and Sawyer and Swiss U. The log of the relative sale price is has a negative coefficient, which means that as the relative sale price increases relative to neighboring apartments, the demand decreases. This makes sense because customers will choose the apartment which has a lower price if the other characteristics, such as the size and number of bathrooms, are the same. So bathroom per square foot is a very positive change. So apartments which have more bathrooms per square foot are highly. So let me just say that customers greatly prefer having a private bathroom. When adjusting the number of bathrooms by the size of the unit, more people applied to apartments which had greater number of bathrooms relative to the size of the apartment, of the unit. Finally, student apt. So students are 63% more likely, or units which students apply for have 63% more applicants than those without students. So this is really just apartments during July and August. We didn't have precise data on students' demographics. We didn't have precise data as to which people were students, but relied on the fact that most student apartments change hands during July and August. And here I'm using the language apartments. To be perfectly correct, though, it would be better to use the word units, because this entire analysis is on the per unit level. However, if you're just explaining this to someone, that's getting a little bit too technical. Simply saying apartments which are larger have more people who apply for them, or apartments which don't have air conditioning have fewer people to apply for them. That's perfectly fine. Again, the point here is just to be to the point quickly, to use non-technical language. So let me just make this more readable. I'll need to increase the size of these boxes. Some of these explanations are too long, so I'll have to simplify some of these. Yes. So I would just take this comment about students and move this into its own section. Also move this into its own section. Actually, I take that back. Instead of what I'm going to do is just make this table bigger. It's important not to spend too much time on these types of formatting things. Anything that you can do to save yourself time will always be understood by the grading team. They're really just trying to help you, and as long as you show that you understand what you're doing, the formatting is not that important. As long as it looks somewhat professional. So this is what I'm talking about here. So the table is too wide to fit onto the Word document. So what I can do is just make the font smaller and then make the table narrower. Delete. Sometimes I need to press the backspace button, and sometimes I need to press the delete key. This looks much better. Now this can be shown on the page. Business, say impact on the business, on new business, on the number of applicants. Say percentage impact on applicants. And say interpretation, business interpretation. Okay. Using this data, so we can tell you which factors contribute. Here are the factors which impact how many people apply to sign a lease. So once I've written out the interpretation of the GLM's coefficients, I will also want to see the variable importance. This is very useful for the interpretation because the signs of the coefficients will tell you which factors increase or decrease the number of applicants, as well as the percentage by which that will change. But those don't consider the interaction effects that the random forest is able to pick up. And so in some cases, those can be different. So I'll go back up to the results of the random forest and just summarize the top 10 variables. I wouldn't include the graph within the executive summary because it would be too complicated to try to explain what the actual values are. In this case, it's percent increase in MSE. But just including the ranking is sufficient. So here I can see that the sale price per square foot is really the most important variable. And then central air, garage type, and student apt are all also important. And then lower on the importance list are the bathrooms per square foot, neighborhood, total bathrooms, and so forth. So I'll just include this as a list. So I'll say we measure how important each variable is in predicting the number of applicants and rank them from highest to lowest. This can help your property management team to prioritize the most relevant info when going after sales leads. The top 10 variables were sale price, whether or not the apartment has central AC, if the apartment has a built-in garage, if the apartment is rented by a student, if there is a detached garage, the number of bathrooms per square foot, if the apartment is in the Sawyer neighborhood, the total number of bathrooms, the total square feet, and the log of the relative sale price. So I'll say the sale price relative to the sale price other apartments in the same neighborhood. Once I have this information, I will then go back through the specific tasks. So I'll go up to task 1 and say that we began with the data and performed cleaning to make sure that it was appropriate for modeling. We used the info from the number of units in each apartment so that these results can be interpreted for each unit individually. Each unit had between 0 and 7 people apply for it. Then we looked at several different histograms and summary statistics. I would say this as we checked that each of the values made sense given your descriptions of what the fields represented in the data dictionary. We wanted to consider the sale price relative to the neighborhood because there is usually significant variation in price depending on the geography. To do this, we divided the sale price by the average sale price in that neighborhood. So again, we did that in task 2. And then in task 3, we gathered insights from the marketing manager to expand on our analysis in 3 ways. These were: 1, the size of the unit determines the price. We calculated the sale price per square foot for each apartment unit so that larger apartments have a lower price, so that larger apartments with a lower price will stand out, as well as smaller apartments which have a higher price. 2, many apartments have their leases end in July and August as students are moving in at the beginning of the academic school year. And so we flagged these apartments as being student rented. 3, people like having a private rather than a shared bathroom. And so we looked at the number of bathrooms relative to the size of the unit. Units which have a greater number of bathrooms per square foot turned out to have more people apply for them. We discovered several errors with the data related to the type of garage. There were 15 records which we needed to remove because of a recording error. We can follow up with your data team to see if these records can be corrected. Now we've moved on to task 5, which was selecting the GLM parameters. Now it's important here to be able to abstract the modeling language into simple terms. I would say something like, we tried out several different types of model. The first was a generalized linear model. This can help you to understand the relationships between each of the variables and the number of applicants. GLMs are a commonly used type of model and are model that can be explained using simple arithmetic while also being powerful in certain use cases. So we chose the type of GLM based on the description of the data for counting the number of applicants as well as making the result easy to interpret. And then we used the offset unit of exposure. We adjusted each record for the number of units that are in the apartment building using a statistical concept known as an offset. Then we fit the GLM. So we then validated that the model was working by splitting the data into 2 groups and testing out the result, testing out the model on a blind set, on a blind group of apartments. This showed that our statistical assumptions will also apply in the real world when you use the results on new apartment buildings, new apartment listings or buildings, or new apartments, which are not represented in this data. We then used an automatic procedure to remove variables which were irrelevant to the problem, known as stepwise selection. This resulted in a simpler model, which was also powerful. So here we fit step AIC. And then we created the bag tree model. The next type of model was based on decision trees. These have the added benefit of taking it into consideration how variables interact with one another. Let me just say these have several advantages over the GLM, and in some cases can be more powerful. And so we wanted to give you another option. We wanted to give our client another option. Trees are able to detect more nuanced relationships within the data, such as interaction effects, which is when multiple variables work together to change the number of people, change the number of applicants, as well as non-linearities, which are when the variables do not affect the number of applicants in a consistent way. Rather than just use, I'll say, to improve the performance, we used a technique known as bagging, which combines the results of, which combined the results of 8 separate models into a single model finally, we fit a random forest. Lastly, we used a common machine learning algorithm known as a random forest, which this is a tree-based model which requires very little customization while still delivering high performance. This also let us determine the relative predictive power of each of the variables using the variable. Yes, so this also let us determine the relative predictive power of each of the variables. And I believe that I actually left out the lasso. Yeah, task 8. We wanted to find variables which were not needed. And so we used a model called a lasso, which stands for least absolute shrinkage something. I don't remember what the acronym is. Least absolute shrinkage something. I'll just say we used a model called a lasso, which automatically removes variables which are not predictive. This showed us that the year sold, total number of bathrooms, and whether or not the apartment was in the Gilbert neighborhood are not important variables. So, you can make your data, our client can use this info, to reduce the costs of gathering data in the future. Okay, now let's go back to where we were. So last week we used the random forest and we measured the variable importance. And now we have to make a recommendation for which type of model we would use. So I would go down to task 11 here. We compared. So we recommend, so which one, so in this problem, what is the goal? Is the goal predictive power or is the goal inference? In predictive power, you really only care about the performance metric, whether it's log likelihood or R squared or root mean squared error. In the case of inference, if the client just wants to understand the business problem, then you want to recommend a model that's easy to interpret, like a GLM or a decision tree. In our case, the problem statement isn't really clear, so I would make a two-pronged recommendation. I would say, depending on your goals of our client, we have a model for a model which can help. If the goal is to be as accurate as possible, then we recommend the random forest. If the goal is to easily explain the results using a spreadsheet, I would recommend the lasso. So there are some other considerations that we could use. So I could talk about like the different things that we could try. To expand upon this analysis, we have several recommended ways of further improving the model results. This analysis clearly shows that the demand for an apartment can be predicted based on the demographics, based on the characteristics of the apartment. Each of our models were statistically validated using a blind holdout set, and we were able to and so we are confident that the resulting models can be deployed in real life, in real time, to help your management team to better serve their customers. It's always a good idea to think about the potential limitations of this analysis as well. There are several limitations to this analysis. And then just think through all of the variables that you used or the types of models, and consider anything that you didn't try or any assumptions that you had to make. So for instance, when we were identifying if an apartment was student rented, we only considered the month that it was rented in. If it was in, we only considered whether or not it was rented in July or August. If we had data on the demographics of the customer, we could use this info precisely. These models are dependent on the geography and can only apply for apartments around the North Ames area. If these results to be used elsewhere, new data for that region would need to be collected. Similarly, this data is several years old, as the latest records only go through 2011. Apartment demand, the market for apartments has undoubtedly changed since then, and so we recommend getting new data. When we were training these models, remember, we only tested a few different combinations of parameters. We only tested a limited number of parameters when fitting these models. We can improve the performance of the models. We can improve the performance by testing out a broader range of parameters if this is necessary. And finally, for the I would also mention that for the GLM, although the model is simple, we did find that the normal QQ plot did have some errors. These quantiles do not perfectly match a normal quantile, and that can make the interpretation difficult or questionable. When fitting the GLM, we noticed that the diagnostics of the model were not ideal. This indicated that the statistical assumptions do not fully match the data. We recommend trying out variations of the GLM to see if a better version can be determined. To see if better results can be found, can be achieved. Now I will go through and just check for grammatical or formatting errors within the executive summary. So I'll just go up to the top and then go to review. And usually there is you don't have, so I'll just go up to the top and then find any words that are underlined, and then right click and then correct the spelling. So our client, so I won't read all of this aloud, but you should at least read through it once. And then just double check the spelling. Next, I want to just look at the number of words. Ideally, there will be at least 2,000 words, but more is always better. So here there are only 1,700 words. So I would go back and just try to add some more descriptive sentences. So I'll just go back through, let's go back to the project statement and really try to make sure that we're hitting all of the bullet points that the grader is expecting to see. So the client is a property management firm and they need to help them attract more tenants to their apartments. This will help them to increase their profitability by signing more leases. So let's try to find ways where these analysis would help to increase profitability. So here are the factors which impact how many people apply to sign a lease. This can be useful for your sales team to help them understand why some apartments may have many people apply and others have only few people apply. So I would try to find some, like maybe a few apartments that have maybe just like an example or two. You know, like some examples of how you could use these results in real life are below. So like I'll just take like 2 records and then based on the variables make some recommendations. So let's just go into like the data here. And actually let's just do head df3. Let's just take the top 3 records. View head df3. And just copy this over to Excel. And then just I'm just going to delete the variables which I know are not that predictive, like year sold, overall quality, lot area, central error I know is important. Delete this. I'm also going to delete all of the garage types and all of the neighborhoods because these take up a lot of space. It's interesting that this 3rd apartment doesn't have values. Well, let's just use the top 2 then. So like this 1st apartment only had 1 person apply to it. There are 3 units. And I can see that these variables are actually out of sync. So this first row should be shifted over there. So there were 3 people who applied to this apartment unit. So let's say this is apartment A and this is apartment B. So if the sale price per square foot is too high, we recommend using a lower price so that more applicants will apply for the unit. If the apartment includes AC, add on an additional fee, add on an additional dollar amount to the price. Really, you should go after apartments that have, we recommend purchasing new apartment buildings which have attached garages and avoiding apartments which have built-in or detached garages, because these were less desirable. We recommend adding more bathrooms to apartments which have shared bathrooms. You could even add even adding a half bathroom, or making a bedroom smaller, even adding a half bathroom to a large bedroom would help if the we also recommend considering the sale price of the neighborhood. Finally, we recommend considering the geography closely and pricing so that your apartments, so that the price is competitive with other apartments in the area. So I think that, so let's just continue to read through. With all of the time that you have left on the exam, just continue to add to the executive summary. It's also not a bad idea to take your document and then just press knit to RMD, knit to HTML. What this does is it will help you to identify any errors. Now, this is really not required. The project statement says that your report is expected to run from start to finish. However, what you're really graded on is not the the resulting HTML file. You're really graded based on the Word document. So first and foremost, make sure that you have all the info that you need in the Word document. So here I can just check. I just ran the output, and then I can just like check that it matches what's in my document. So let me open up the template and just like spot check a few of the coefficient values. So I'll just check like the log likelihood here. So let's go to the tree, look at the AIC. Yeah, 3, 5, 6. Yeah, it looks like 3, 5, 6. go look at one of these GLM coefficients. Just make sure that we have the right GLM selected. This is the step AIC GLM. Let's go up to the original GLM. So let's see, years sold, it's minus 2.805. Years sold, minus 3. Oh, so this is actually slightly different. A month sold is minus 7. Month sold is minus 7. Overall quality is minus 4.2. Minus 4.2. Total square feet is 6.21. This is also 6. So it looks like these are slightly different. If I have a lot of time left, I would think about updating this, but you also have to consider that if you update this GLM, you also have to update the step AIC, and then you have to update the whole table, your coefficient table here, and then you also have to update your executive summary. So really ask yourself if that's worth the time, if you think that would really impact your grade. Personally, I think it's more important that the results of your report are consistent, that the signs of your coefficients agree across your Word document. If there's some variation in the HTML document, I think that this is secondary. Let's just look at a few other things. We looked at the GLM, we looked at the bag forest. Let's look at some of the features. Here's a sale price over relative sale price. Looks to be the same. It's also a good idea to look again at the points. So just look at the number of points in each task and make sure that you are hitting any of the points that have a lot of value well. Like task 2 is worth 10 points. Explore the predictive variable neighborhood, sale price, and overall quality. So let's just make sure that you have those variables. So there's number of units, sale price. What about overall quality? I want to be sure that I include this graph. So neighborhood, sale price, and overall quality. So there's neighborhood sale price. So I would just maybe grab some of these graphs and put them into the report. So there is overall qual. And it looks like I failed to include the overall quality. So let's just add this in quickly. The overall quality measures the state of repair of the apartment. This ranges from 0 to 10 and is approximately symmetric So no transformation is applied. You can also look at the mean. Where's the mean? Here are the mean values. I'll just look at the summary of the overall quality. This has a mean of 6.082. Unweighted. And if I want to get the weighted mean, I can just take this and get the and take the sum of the number of units times overall quality divided by the sum of num units. So this has a weighted mean of 6.06. And what was the other variable? Oh yeah, neighborhood sale price. So let's just make a histogram of that. So I'll go up to my histogram code. Here's a histogram. And just show the neighborhood sale price by itself. And saying neighborhood sale price isn't in the data. I believe that's because we removed it. That's okay, because I think that I included neighborhood sale price here already. So let's just go back through the project statement. So that one, neighborhood sale price, overall quality, that looks good. Insights from the marketing manager. Yes, I remember we created 3 features. Inspect the garage type variables. Let's just check. Yep, it looks like I removed the 15 records. Select the GLM parameters. This is worth 10 points. So I want to make sure that I've hit each of these bullets. Explain prior to fitting model why your choice of response family is best. Yes, I say that's the Poisson. Choose a link function so that the model will be multiplicative. The log link is the only, yep. Choose an offset term, if any, so that the model will predict the sale price. The offset term, yep. Choose a weighting term. I don't need to use a weighting term, yep. So it looks like I'll get 10 points on this. Task 6 is actually fit the GLM. So construct the GLM, use all predictive variables, yep. When you are done, provide the output of the coefficients, p-values, and AIC. So yes, I have the AIC, I have the coefficients, I have the p-values. And then